Alright, class. So far, we've gone over several different kinds of sorts. Everything from insertion to shell. Today we're going to talk a little bit about quicksort as our next sort. Now I'm just going to open up the project we've been working with, and I'm going to use that. So effectively, we're just going to copy and paste the stuff in here. Now we could actually make an object out of this, file, new Java class, and I could just make a sorter. I could create it and have that thing sort it. But for the sake of ease, for just showing this off, we're going to do it all in one file here. Perhaps at another point in time, we'll talk about how we could make all these into some sort of sorting object if we wanted to. All right, well first, before we get into the big issue here, let's see what quicksort actually looks like when it runs. So we'll pop open a couple of them. You got random, nearly sorted, reverse, unique, all that good stuff. And I'm just going to run it. Now, first thing I want you to notice, when we do this, notice how it seems to kind of split it in half. What this thing does is it actually finds kind of a pivot point. Run it again. And it's going to move anything, basically say smaller than that pivot point, higher. Anything larger is going to go lower. So it's going to kind of almost sort everything. You'll see this really good in the reverse. If I hit that once or twice. It finds a nice little midpoint. It, moves everything smaller above it, everything lower below it. Then it's somewhat sorted. Then it goes through and actually sorts all of these. Now, quicksort and merge sort are a little different than the loop sorts we've been discussing. Because these use what's called divide and conquer. The easiest way I can use to describe divide and conquer, imagine if I told you to go paint a fence, and that was going to take you like an hour to paint this big fence. Well, I decided to send someone else to help you, and they were going to do half the work. Well, now it should take roughly 30 minutes, right? If I send 3 more people to help you, well, that 30 minutes should be 15, right? If you all do the same amount of work. That's essentially what divide and conquer does. We split up a problem and we, take it into smaller pieces basically. So if I come back here and I make this a little bit larger, let's say, and I just want to see quick for right now. Take a quick look. There we go. It moves everything smaller up, everything larger down, and then it sorts the top, sorts the bottom. Or middle, bottom. It may split it up into multiple sections depending on the algorithm you're using. And as you can see, some work better than others, like view unique seems to not be as great as the others, but for the most part, if we ran all of these, quicksort would be one of the first ones to finish. Merge sort as well. These are 2 of the fastest sorts you're going to get. So let's take a look, now that we kind of have an idea of how this works, of what the code looks like. Magnifier. There we go. It helps if I spell things correctly, though. There we go. All right, so, boop. Now just below my print, and actually above, and I got some other stuff for the next lecture, bubble sort and everything. I just put this at the top, basically. This is quicksort. I've got an array, well, an integer called length, and an array that I'm going to use for quicksort. And this is going to be a global variable. So you can just make a little comment here. Now this has 3 parts. You'll see there's 3 methods. There's qsort, which takes in the array. This is typically what we are going to call. We have quicksort, which is going to do our sorting, or splitting, I guess you can say. And exchange numbers is going to do the exchanging of numbers, moving them back and forth. So we got 3 different little bits here. Now another thing you're going to see with these 2, I guess you can say, sorts, uh, one would be, the keyword would be recursion. Basically, recursion is when a method calls itself. Now for quicksort, notice that when we run this, boop, it splits things up. Basically, it's going to split this up into little bits, and it's going to keep calling quicksort until everything's basically arranged how it's supposed to be. So let's take a look at that first one here. Public static void qsort with our input array. And actually this right here is just kind of a helper array for us. It's not actually the array we're passing. This is the array from the main that we're going to pass, that we're going to sort. Now notice that this is remarkably short, right? And this is just a quick little check. If that array is empty, then leave, basically. I know this is a void, and typically we don't have returns for voids, but you can just return, and it will leave this method. It'll stop running, basically. So you can actually use this to just stop, basically. Of course, we could just say else here, and we would get kind of the same effect for the most part. If I put a little else around this, if it ran to this would just be nothing. You would get the same thing basically happening. Now, I set my helper array to be set to this input array. I set the length to whatever the length is, and then I'm going to call quicksort. And notice I say 0 and then the length of the array, basically. If our array's 10, right, this says, 0 to 9, which is going to be the beginning and the end of the array. Now this is where the recursion happens. This is basically the entry point. I come in and I pop into quicksort. I pass it a 0 and a 9, so the beginning and the end of the array. And this is the longer part of the project, so let's open this up real quick. Now, you'll see I set a variable to the lower and a variable to the higher. And then I do some math. If you remember, I told you there was a pivot value involved. Basically, we're kind of picking the middle number, and we're going to move everything, as I said again, smaller above it and larger below it. That kind of pre-sorts the array. And anything that's pre-sorted, if you watch all those animations, things that are already somewhat sorted are always faster. So we have a couple of simple loops. And notice these loops, the only thing they're doing is basically just going in until they find a value that needs to kind of move. And once we find a value that needs to move, this needs to move up, this needs to move down, we will exchange those numbers with the locations that they're at. We start from one end, we start at the other. And once we've done that, we bump these up and down again. And then this loop may keep going until we get to the middle, basically. Basically, this whole thing right here is just moving these numbers to where they're in the appropriate positions. Now, bigger down at the bottom, smaller at the top. That's what this whole motion's about. We scroll down, and this is where we have our recursion. Now notice this is going to call quicksort again, this very same method that we're in, but it's going to give it different numbers. The lower index was 0, but J, at the start, J is the higher index, but we're going backwards. So, if it's 10, the last item would be 9, right? 8, 7, 6, and as soon as we find, 5 or something like that, well then this would basically be 0 to 5. This right here would be, 5 to, or 6 to 9 or 10 or whatever. Basically what this does is it's going to split that array in half. And then we're going to sort the top half of the array, basically find a pivot value, move the smaller ones up, the larger ones down, and then we're going to come down here and we're going to split it again. And we're going to keep doing this until we've sorted everything. So basically how quicksort works is it takes this array and just keeps breaking it down until it can't do it anymore. And then everything's sorted. Now, notice this exchange numbers here. I'll go ahead and bump that open. It's just a couple of lines. All it is simply just a swap, a juggle. I say this number plugs into here, and then I swap it over. So pretty simple. This quicksort is where the bulk of everything happens, and it's going to happen a lot. If we did a bunch of print statements, you would see it actually kind of recursively calls itself, well, a lot of times. If you want to dare put a little print statement down in here, you could, just to see how many times it gets called, depending on the size of the array. But this is quicksort. You see, it's a lot more complex than, let's say, our bubble sort or something like that. But it has to be. But it's also significantly faster. So, we've got our array. We give basically the whole length of the array, bottom to top. We set some numbers. We split it in half, basically, and we start figuring out where these numbers need to go. We exchange them when they need to be exchanged. So we're moving the bigger ones down, the lower ones up. And then once we're done with all that, we split the top half in half again, and we split the bottom half in half again. And then we do this whole thing again. We'll sort those. The smaller at top, the larger at bottom. We'll sort the second one. And we'll basically just keep breaking it up and recursively calling it until this thing is sorted. Right there. So let's take a look and see how quick this is. We'll just go ahead and, whoop. I've got qsort here. I've still got my timer from the previous programs. This gets my system time, this ends my system time, and this tells me exactly how much time has passed. So, plus milliseconds. So let's take a look. I've got 2 million here, I believe. So let's see how long it takes to actually sort 2 million. And, well, tell you what, let's make this obvious first. We'll make 20. I'll print it just so we can know it's sorted. It's always a good idea to check that. Alright, we run it. Oh wait, I didn't print. Did I print A? Let's see. Oh, that should have printed A. Why are you not printing A? Let's see. What did I mess up? Print. Yeah. There's my array. It's filled. Hmm. Oh, that's weird. Well, let's do it this way then. Arrays dot toString A. Okay. You're not listening to me at all. Well, let's see why that is. Well, it took 700 milliseconds to sort 20. That seems off. What am I running? Maybe I'm running the wrong file, perhaps. Let me see here. What's this thing's issue? If I increase this to a bunch, let's just say 20 million. It takes the same exactly amount of time. That's peculiar. I seem to be having some issues here. Because it's not printing. Actually, it's not even printing the milliseconds that I added. Well, I think we've run into one of those fun errors where the program is confused, so to speak. So let's do this. Just close that real quick. And we'll reopen the project. And let's hope that everything I typed in is still there. All that code is still good, so you don't have to worry if you wrote all that down. But boop. And we'll worry about that next time. Alright, so we just need this. So let's see. It's there. There we go. Okay, perfect. Now, it seems I have a lot of zeros here. And I made this a little too big for us to see, so let's dump that down a little bit. There we go. Oop. Okay, there we go. Now, you may have saw a lot of zeros. I had 20 million. The odds of a zero getting picked out of 0 and 999 is there's going to be a fair number of zeros in there. But if we take a look, we make it a slightly smaller range, we see that it is indeed in order. Okay. So since I know it's in order, and now it's working again, thankfully, we'll go ahead and adjust. And it took next to no time at all. We go up to 200,000. 14 milliseconds, okay. Add another 0. 95 milliseconds. That wasn't a huge bump. We add another 0. And now we are up to 20 million. Oh, wait. Oh, look at that. It took almost a second to sort 20 million. And 200 million. Now, there is a max size, depending on your NetBeans, of how big your array can be. The set size is generally going to be like 2 point something billion, but usually memory allocation won't allow anything near that big. Maybe, probably not as even bigger than 500 million, but there we go. It took almost 10 seconds. Of course, it had to fill it and do some other stuff, so you notice there's a slight discrepancy, but 200 million numbers completely sorted in under 10 seconds. Now, if we were to do this with bubble sort, I hope you got some popcorn, because it's going to take a significant amount more time to do that, basically. So this gives you a good example, I hope, of how all these methods we're going through, all these different sorts, do exactly the same thing, but there's just a real wide variety of how much time it takes and how efficient they are. And even if we go a little bit further, and you may notice there's a little picture here. My little girl watches cartoons. But here we go. Even if we look at this, individual cases, some of these algorithms do better for when you're reversed, when you're nearly sorted, when you've got these odd, unique cases and stuff like that, where you're completely random. Some do better versus that. Particularly with these lower sorts, you'll see like one may do random better, but another, completely doesn't care if it's backwards or not. And another will absolutely get your worst case time if it's backwards. It just depends on how these sorts approach things. Now, that was quicksort. Our next sort is going to be merge sort, which is a little bit different, but again, it still sorts the same, just like everything else. It's just the code's going to run a little differently. All right, well, if you have any questions or issues, let me know. Otherwise, that is merge sort. Or, I'm sorry, that is quicksort. Merge sort will be the next video.